yesterday we started looking at multi-component systems. We initially started out with the ideal gas, and since we are doing everything in terms of the chemical potential, we had written down the chemical potential expressions for an ideal gas, which we had already seen in the earlier module, the third module. And then we said that the real gas, in the expression for the real gas, you replace the pressure here, mu equals mu naught plus RT ln P, where mu naught is a function of temperature alone. This was for an ideal gas, and when you write it for the real gas, it becomes mu equals mu naught plus RT ln F when and F by P tends to 1 as P tends to 0. And then we looked at something called perfect gas mixtures and imperfect gas mixtures, and then we looked at something called ideal gas mixtures and non-ideal gas mixtures, and with that formulation we saw that we could expand them or extend that to ideal mixtures of liquids and solids as well as non-ideal mixtures of liquids and solids. So, it is essentially ideal gas, real gas, that was the initial formulation where we went from P to F, and then we used the perfect and imperfect gas mixtures. That is only a concept which we will kind of borrow on from time to time. So, let us keep it aside for the time being. We will go through it and see how we defined it in a little bit, and then we went into real gas mixtures and ideal gas mixtures and real gas mixtures, and then we saw that we could extend that formulation to ideal mixtures of liquids and solids as well as non-ideal mixtures of liquids and solids. So, we have already seen this. The ideal gas is mu equals mu naught plus RT ln P, and for the real gas it was mu equals mu naught plus RT ln F. And the concept wise, the perfect mixture of gases is something for which the following can be used as the definition of as the chemical potential for every component I. Mu equals mu I naught plus RT ln Pi. This is the partial pressure of the component I in the gas mixture. And then for the imperfect gas mixture, then we said we should replace this partial pressure with Fi hat, the fugacity of the species I in the mixture, mu I equals mu I naught plus RT ln Fi hat, and to complete the definition, Fi hat divided by Pi tends to 1 as P tends to 0. The fugacity coefficient for the species I in the mixture becomes Fi hat by Pi equals Phi I. The earlier one, the pure gas fugacity coefficient, we had defined as F by total pressure P as being equal to Phi. Therefore, we could write mu equals mu I naught plus RT ln Phi I Pi for an imperfect gas mixture, and if we expand Pi into Pyi, total pressure into the mole fraction, we get mu I naught plus RT ln Phi I Pyi as the expression for mu I. And then this one is what we need to focus on. In the ideal gas solution, the formulation that we had used is mu I equals mu I hash plus RT ln Yi. The important thing being that mu I hash is a function of both temperature and pressure, and here we have a convenient formulation in terms of the mole fraction, mu I equals mu I hash plus RT ln Yi, and this is for an ideal gas solution. For the ideal solutions of liquids and solids, we use Xi as the mole fraction of the component I in the liquid or the solid solution. Then for the non-ideal gas solution, I had earlier said real gas solution, make it non-ideal gas solution, we write mu I equals mu I hash plus RT ln Phi I Yi. This Phi I brings in the non-ideality of the component in the gas solution, and for the non-ideal liquid or solid solution we could write mu I equals mu I hash plus RT ln gamma I xi, and gamma I tends to 1 as the mole fraction of the component I tends to 1. So, this is what we had essentially seen yesterday and reinforced, and again reinforced this morning in this class. Then we found that the definition, especially for the non-ideal liquid and solid solutions, work well in most liquid cases, liquid solution cases, whereas when the component happens to be either a gas or a solid at the temperature and pressure of the solution in question, then we may run into some difficulties, because as we change the mole fraction of the component in the solution, the phase could change, and therefore we had to come up with a different formulation. We had used a 2 equation formulation for that. For the solvent we had used a subscript O, and the solute we had used a subscript I, and therefore we could write for the solvent mu O equals mu O hash plus RT ln gamma O XO, along with the completeness of this gamma activity coefficient. Gamma O tends to 1 as XO tends to 1. This is for the solvent, and for the solute mu I equals mu I hash plus RT ln gamma I xi, and gamma I tends to 1 as xi tends to 0. This was equation 4.9, and this is where we had finished up yesterday. Now let us return or look back at ideal solutions for a little bit. We are going to develop something important here. So let us concentrate on ideal solutions. You know that equation 4.2, you can go back to your notes, it is already given here, mu I equals mu I naught plus RT ln Fi hat. This works for the ideal solution case, where mu I naught is the function of temperature alone. Now we know that ideality is nothing but a special case of reality. Therefore, the expression for the real case must also be valid here. If we write it for the real case, it should be valid for the ideal case also. It is always the super thing should include the special case also. Therefore, this 4.5 equation 4.5 mu I equals mu I hash plus RT ln yi, mu I hash is a function of temperature and pressure. This equation should also be valid. Now from equation 4.2, just by transposing this equation mu I, or in other words subtracting mu I naught from both sides, we get mu I naught equals RT ln Fi hat, and doing the same thing to equation 4.5, we could write mu I equals mu I hash mu I minus mu I hash equals RT ln yi. Now what I would like you to do is just subtract the second equation from the first equation and tell me what you get. Okay, take about 5 minutes. It is good to juggle your little bit your brain and your hands and so on and so forth. So just work this out, subtract equation 2 from equation 1 and tell me what you get. 5 minutes please. if you subtract equation 2 from equation 1, you would get mu I hash, this is the minus mu I hash here, therefore mu I hash minus mu I naught equals RT ln yi minus RT ln fi hat. So ln A minus ln B equals ln of A by B, therefore this becomes RT ln fi hat by yi. Same equation here. Now note this argument a little carefully, we will be using this argument a few more times in this particular course. You see here mu I hash mu I naught, this is the left hand side of the equation. You know that in any equation whatever applies to the left hand side must apply to the right hand side. So we will look at dependencies here. Mu I hash is a function of temperature and pressure, mu I naught is a function of temperature alone, and fi the left hand side therefore is definitely independent of composition. So that is clear here, and therefore the right hand side must also be independent of composition. Let us look at that point alone, it has to be independent of composition. Therefore see this is R, what is on the right hand side, R and T here, there is no problem here. If at all we need to worry about composition, it has to be in this term. This ratio fi hat by yi on the right hand side must remain constant when the composition is changed, because you have a left hand side which is independent of composition, therefore when you change yi here, the only way that this remains independent of composition is that this ratio becomes independent of composition. Therefore fi hat by yi must remain constant when the composition is changed, or when yi, which represents the mole fraction, is changed. I hope this is clear. Fi is the fugacity of the pure component I at the same temperature and pressure as that of the solution that we know, or in other words Fi is Fi hat when yi equals 1. Now Fi is pure component, Fi hat is the fugacity of that component and solution. Now Fi can be considered as Fi hat when yi becomes 1. Now you know where I am getting at. Therefore Fi hat by yi is nothing but Fi by 1, which I have written as Fi, or Fi hat equals yi into Fi directly by transposing this equation. We will call this equation 4.10. This is something powerful, and before I go forward, let me go through this argument once again, because we will be using this argument a few times. We have a quantity here on the left hand side which is independent of composition, therefore the right hand side must also be independent of composition. The only term that changes with composition is this, therefore this has to remain constant when yi is changed between the ranges that it can take. If we look at one particular value there, which is when yi equals 1, Fi hat by yi must equals Fi by 1, that the because when yi becomes 1, Fi hat becomes Fi, and therefore Fi hat equals yi into Fi. This says something powerful. It says in an ideal gas solution, we are looking only at ideal gas solution, remember that is what we decided to focus on earlier. The fugacity of each component, which is represented as Fi hat here, is equal to its mole fraction yi times the fugacity Fi, which is what it would exhibit as a pure gas at the same temperature and pressure as that of the solution. To repeat, in an ideal gas solution, the fugacity of each component Fi hat is equal to its mole fraction times the fugacity which it would exhibit as a pure gas at the same temperature and the same total pressure. This is something powerful. What has it given us? It has given us a way of estimating Fi hat if Fi is known, and this is called the Lewis and Randall rule. This name you may have heard, it is called the Lewis and Randall rule, which essentially says that Fi hat equals Yi times Fi. And as mentioned, the Lewis and Randall rule allows us to know the fugacity of a component in the mixture by knowing the fugacity of the same gas at its pure state, which is quite powerful. Now, we will look at something called partial molar properties, which are essential whenever you consider any mixtures or solutions. Let us start with the Lewis and Randall rule itself. From the Lewis and Randall rule, which is valid for an ideal gas equation, we can expect that in general the property of a component I in a solution may not be the same as the pure state property at the same pressure, at the same temperature and the same total pressure. Therefore, we cannot use a weighted average. What we did in the case of the ideal gas solution is that we used a weighted average. Fi hat equals Yi times Fi, Yi was the weighting factor there. Here if it is a non-ideal solution, we cannot do that. We can do that only for an ideal gas solution. Therefore, we use something called partial molar properties. To know what partial molar properties are, let us take M superscript T, Mt, to be any extensive total thermodynamic property. Okay, we have seen this already. For example, it could be Ut, which stands for the total internal energy, St total entropy, Ht total enthalpy, At total Helmholtz free energy, Gt total Gibbs free energy, or Vt total volume. If this is the case, then the partial molar property, which I am going to represent as MIT with a hash over it. MIT is the total property, is the property of the component I in the total solution. With a hat, it becomes a partial molar property. It is defined as equal to dou Ni of Mt at constant temperature, pressure and all other mole fractions remaining the same. Again, MIT hash, the partial molar property, is defined as dou Ni of Mt taken at constant temperature, pressure and all other mole fractions remaining the same. We will call this equation 411. This will become clearer as we go along. And as we had said earlier, the partial molar property may not be the same as the pure state property, the same temperature and total pressure. That is a reason for defining something different as the partial molar property. It is the property that it seems to exhibit when it is present in solution. In other words, it is some sort of a hypothetical measure. Why are we using this measure? It gives us an easy means of calculating the total property or estimating the total property. The total extensive property in turn can be computed from the partial molar properties as Mt is nothing but sum over mole fraction Ni times the corresponding partial molar property MIT hat. So, this is a simplistic formulation To be able to do this, we go in for some sort of a conceptual partial molar property. What I would like you to do is take a few minutes and write down this expression for each one of these partial molar properties that we have seen so far. There are about 6 here. Please write them down for each of those properties, this expression. Go ahead and I will present them in the next 5 minutes or so, after 5 minutes. Go ahead please. you would have found it reasonably simple to write this down. Vt total volume is nothing but summation of Ni times partial molar volumes. Ut is nothing but summation over Ni times partial molar internal energies of each component. St is nothing but summation over Ni Si t hat. Ht is nothing but summation over Ni Hi t hat, the partial molar enthalpies times the mole fraction of each enthalpy summed over all i's gives you the total enthalpy. At is nothing but sum over Ni At hat, and Gt is nothing but sum over Ni Git hat. It is nice to have this here. You can refer to this from time to time. Equation 4.13. The dashes are somehow not visible in some cases. Please make sure that these dashes are present in all your quantities. Now, we have already seen this, that the partial molar property is defined as dou Ni of Mt at constant T, P and J. Does this remind you of something that we have seen earlier in the earlier module? Think about it. If any extensive property can be written as a function of T, P and Ni, then the total differential can be written as, this is again an exact differential. Therefore, you could write the total differential dmt, or this is a state function. Therefore, you could write the total differential as dmt equals dou t mt at constant p ni dt plus dou p mt at constant t ni dp plus summation over dou ni of Mt at constant T, P and J. Here we had taken Mt as a function of T, P and Ni, or what is this? This is nothing but the partial molar property. Therefore, dou Mt dou T at constant P Ni dt, dou Mt dou P at constant T Ni dP plus the partial molar property, the sum of the partial molar properties times the dni for each species. That is the total differential here. We will call this equation 414. The total differential from equation 412, which is this, Mt equals summation of Ni times the partial molar property of I. You take the product of each and sum them over, that will be equal to the total value, the total extensive property value. This is equation 412. If we differentiate this, we get the total differential dmt equals summation of Ni times the partial molar property of I plus the partial molar property times dni. This essentially comes from using the chain rule here. Sum over each one of these terms, you could do the chain rule for each of these terms and then separate the terms, group them appropriately to sum them over Ni dmit plus summation of mit dash dni, essentially chain rule application. So, we have the total differential from this expression 414 as this on the right hand side, and the total differential here. What I would like you to do is equate the right hand sides of 414 and this particular expression, which is equation 415, and tell me what you get. See whether you get something interesting. Take the next 10 minutes to do that. Go ahead, please. Okay. I had asked you to equate dou t of mt at constant p n I dt, dou mt dou p at constant t n I dp plus summation of mit hat dni with summation of ni times the partial molar of I plus the summation of the partial molar property times dni. If we do this, you can see that one of these terms is going to cancel out, then you should have gotten dmt dt at constant p n I dt, this is the same term as earlier, plus dmt dp at constant t n I dp, again same term as earlier, and what does not cancel and gets transposed to give you minus summation of ni dmit as this term. So, this term essentially gets cancelled with the same term as on the other on the right hand side of equation 414. Therefore, dou mt dou t at constant p ni dt, dou mt dou p at constant t ni dp plus summation of ni dmit, this equals 0. Are you able to see some nice thing here? We will call this equation 416. So, this is if you write it in terms of g, you will see that g is a function of t p and mu. Therefore, you can probably make the connection with something that we have already done earlier. Now, at constant temperature and pressure, this equation 416 that we saw, this we are writing for all partial molar properties. So, if we instead of concentrating on G alone, which we had done somewhat earlier in the earlier module, we will do it for any total property. If we do that at constant temperature and pressure, these two terms are going to get to 0 because dt is 0, dp is 0. Therefore, what remains is summation of ni dmit hash equals 0. We will call this equation 417. If we divide summation of ni dmit hash equals 0 by the total number of moles, each term in the sum gets divided by n, and therefore, each of these ni's can be replaced by the mole fraction. That is the definition of mole fraction, ni by n is the mole fraction. Therefore, when you divide it by the total number of moles, you get sum over xi dmit hash equals 0. This is equation 418. This is quite a powerful equation, as we will see later. I think we are almost out of time for this particular class lecture. Let us stop here and continue from here in the next class.